branch is physical chemistry. Okay, the second branch, it is organic. Now for organic, I've already introduced some of you to organic chemistry, and you've watched the videos of organic chemistry. And in the third branch, it is inorganic. Now all these branches must be equally studied, because they are all examined. Okay, they are all examined and they are all taught, okay, at NFP. Now since I introduced all these ones in the previous lesson for organic, today let me talk about inorganic chemistry. Now this inorganic chemistry, it is the chemistry of all other compounds apart from compounds of carbon. But even compounds of carbon, the carbonates, the carbon dioxide, the oxides of carbon, and the hydrogen carbonates, they are also organic compounds. Okay? So inorganic chemistry is the study of substances other than compounds of carbon, apart from some few, and the few include the carbonates. These carbonates, they are all inorganic compounds. The hydrogen carbonates, yes, that's pretty good. Hydrogen carbonates, they are all inorganic compounds or hydrogen carbonates. And then the oxides of carbon, that one I mean the carbon dioxide gas and the carbon monoxide gas. Now all these ones, they are all inorganic compounds. But the rest compounds of carbon, the rest, now we study them in organic chemistry. Now you may be wondering, this organic chemistry, so the inorganic chemistry, it evolved to solve society needs. And the needs by then was, you get gold, for instance, but this gold, you get it in an impure form, which we call an ore. Okay? An ore, what is the spelling? It is O-R-E, which is called an ore. Now, you won't use the gold in that impure form. You have to find ways, okay, of converting this impure gold into the pure gold, which you can now use to make necklaces, to make rings, to make cars, to make, depending on the society needs. Maybe somebody wants a car that is made out of gold. Somebody wants a necklace that is gold. Somebody wants a ring that is gold. Somebody wants a gold tooth. Okay? But you cannot use gold tooth from an impure gold. Okay? You have to first purify it and get pure gold. Okay? So that you can now solve the society needs. So because of that, okay, then inorganic chemistry was born. For instance, cement. Where do we get cement from? Yes, good, pretty good. Limestone, we get it from limestone. But you cannot just use this limestone the way it is. Okay? And you think you will use cement. So what we do, we get the limestone and we find ways of improving it by heating it with calcium silicate, sand. Okay? In different proportions. Did I say calcium silicate with silicon dioxide, sand, in equal proportions, so that now you get cement. So by doing that, okay, by aiming at solving the society needs, then a full branch of chemistry called inorganic chemistry was born. Is that okay? Yes, remember, if you have a question, you can always drop it in the chat box. Now, you cannot study inorganic chemistry without knowing what a periodic table is. Now, in long times, these elements, they were not known, and they were discovered one by one, okay? So they kept on discovering elements. Imagine, you've started by discovering one today, tomorrow you discover another one. After 2 years, you have 20 elements, okay? Okay, 20, it's not much, you can easily cram the 20. You can easily, Then at the end of 5 years, you have 40. The work is becoming too much. At the end of 20 years, you have 100 elements. Oh my God. Okay? Now the question is, how are you going to study these 100 elements with ease? Like how? How? Hmm? You cram how to prepare all the 100 elements one by one, and all the reactions of all the 100 elements? So it becomes kinda perplex, okay? Kinda hard. That therefore, if you at least classify them, okay, into groups, and you study groups, then it becomes easy for you to study these elements. Is that okay? And so that's what brought this scientist called Mendeleev as early as 17th century, mid 17th century, to arrange these elements into a given order basing on their masses. So this man was smart, you can imagine, as early as 1869. He was able to take the masses of these elements, okay? And he arranged these elements into an increasing order of their masses, okay? And basing on their masses, he was able to establish 8 groups, 8 vertical groups, okay? He found out that for every 8 members, okay, if you count from 1 to 8, there is some repetitive order, okay? He counted, you count 1, 2, 3, 8, 1, 2, 3, 8, the order repeats. So he arranged them into groups of 8, okay? And he named these vertical groups, he named them groups, okay? And this was group 1, group 2, group 3, okay? Group 4, group 5, group 6, and group 8. Then he also, these elements, when they were ordered basing on their atomic masses, they all, yeah. So now, I was saying that you can't write, you are writing group 1 and you write this. Then I'll cross you, okay? This is not group 1. Group 1 is written as, you write 1 in Roman numerals and you, so this is group 1. Group 2, same thing, okay? Group 3, same thing, and so on, and so on, and so on, okay? But, but for periods, you can write period 1, period 2, period 3, and so on, and so on, and so on. And this was from Mendeleev, imagine, as early as 69. However, for him, he arranged basing on the atomic masses. We are going to see, okay? And so now from this arrangement, our Mendeleev was able to find out that when you arrange these elements into these groups, that members in a particular group, okay, they have similar, they show some similarity in both physical and chemical properties. They show some similarity Eh? For instance, that members in group 1, eh, they tend to show some similarity. In fact, they have similar chemical properties and physical properties. For example, if you had to compare melting points among group 1 elements, you find out that they all have high melting points. Uh-huh. If you had to compare reactions, they all react the same way. Okay? And so that similarity, it's the one he called a periodic law. Okay? He came up with a periodic law. And he was like, it states that the properties of elements, okay? The properties of elements are periodic functions of atomic number. Now this one is a revised one. For him, he said, are periodic functions of their atomic masses. However, due to frequent research, which we shall not talk about now, okay? There is one scientist called Mozilla. He's the one who discovered atomic numbers. And so when he arranged these elements basing on atomic numbers, it, the periodic table was fit, it was good. But when you arrange them basing on the atomic masses, you create some anomalies. For example, you find some elements having different masses, but the elements are of the same atom. For example, you know carbon. Carbon has carbon 12 and carbon 14. Okay? These are different isotopes. Now, this one has a mass of 12 and this one has a mass of 14. So where are you going to place these two carbon? Yet they are elements of the same elements. So if you use mass, it creates that confusion. But when you use atomic number, then the atomic number removes the confusion. No two elements can have the same atomic number. Okay? And so that's why from the periodic law, it says that the properties, okay, the physical and chemical properties of these elements are a periodic function of their atomic number. So it is basically as simple as that. So from that, I can remind you a periodic table. So you can see, we have our periodic table, okay? So in O level, you just studied this. This one in O level. You didn't talk about this, then you studied this. This is what you studied, the first 20 elements. But good enough, that was O level. But now here in A level, we shall study all this. Okay? And actually, this is inorganic chemistry. You study periodic table. You cannot do away with periodic. In fact, inorganic chemistry is about the periodic table. And which periodic table? These ones. However, we might not concentrate on this. We shall not concentrate on actinides and lanthanides. We shall not. But mostly these ones, all these ones, we shall study them. But don't get worried. Actually, that worry you have, it is the one which created a need for a periodic table. I know you are worried. You are like, what? How are we going to study all this? And how are we going to study it? So that worry is the one which led to creation of a periodic table. That we arranged these elements into groups. Okay? Groups, and periods. Is that okay? Groups and periods. Now, elements in a given group, they have similar chemical and physical properties. For example, elements in group 1A, they have similar chemical properties. Elements in group 2, the same. Group 3, the same. And so on and so on and so on. So therefore we study them as groups. Okay? So that is the good thing about it. We study the whole of this periodic table, but we study all these elements in a group. For example, we shall see group 1 elements, group 2 elements, group 7 elements, noble gases, groups, and so on and so on and so on. Okay? So there is nothing you should worry about. So anyway, let's talk about the periodic table. So if you can see they are colored, these colors don't mean nothing. Okay? So these ones, they are alkali, they are alkaline metals. Okay? Then these two, these ones in group 2, they are alkali earth metals. Okay? And these ones are in group 2. Then these ones, they are in group 3. Okay? And then these ones, group 4, group 5, group 6, group 7, and group 8. Now these ones, they are metalloids. They are neither metals nor non-metals. They are just in between. Okay? But these ones now, they are non-metals. Okay? As you can see. Then these are noble gases. Okay? Now these ones, they are called transition elements. Not transitional. Let me write it so that you don't make another mistake. It is transition. Transition. Oh, sorry for that. This is O. So they are transition elements. But most students, they usually make a mistake and put
Teacher, which
AM.
ones?
These ones from here, okay? And then
I'm not seeing.
the whole of this. And are you seeing my screen?
Yes, yes, yes.
So the ones
The one in color blue.
yeah, the ones I'm ringing, this box. Okay, it is a transition between group 1, group 2, and group 13, group 3. I hope you can see it is in between. Okay,
Mm.
so these are transition elements. So you can now mute again. Now, let me first erase to show you this. Now, this one, are you seeing this between this one here? Now, these ones, they are called actinides and lanthanides. And this is where they belong, just here, just here. And if you had to compare the atomic masses, they fit in here. Okay? You'll be able to see that the atomic number, did I say atomic mass? The atomic number of barium, I hope you can see, you can't see it. It is just one below the atomic number of arachnide. And this one, the atomic number of this is just one. Actually, you can see this is 71 and this one is 72. Are you seeing that? And this one is 56, whereas this one is 57. So they are placed just here. Okay? And the same applies to this actinides. This is I think this is 88 and this one is 89. Now this one is 104, this one must be 103. So they are fit just here. Okay. Now you just in senior 2, let me take you back. You wrote that, let's say if it is 11, if it has atomic number 11, actually electronic configuration describes how electrons are arranged, okay, are arranged in their energy levels or sub-energy levels or orbitals. Okay? How these electrons are arranged around the nucleus of an atom. Okay? And it is usually in ground state. Let me just take you back to senior. If this is my atom, I think I have my atom here. Let me not complicate things. So if this is my atom, this is the nucleus, okay? And these electrons are arranged in shells, okay? So these are the shells that do surround the nucleus, as you can see. Where the first shell has 2 electrons, then the next shell has can accommodate a maximum of 8. And you remember in O level, you wrote if you have 7, you wrote it as 2. Then what is the balance? Yes, pretty good. 2 to 5. And I hope you can see it from here. So it has the nucleus, then the first shell has 1, 2 electrons, then the rest they do occupy the next shell. Okay? And the next shell is covered by how many? The balance, 5 electrons. Now, that was whatever. That's how simple it is. But now here, we simply go deep. We just don't talk about the shells. Okay? We go deep each shell. Okay? And see that inside each these shells, okay, we have there what we call orbitals. Okay? Inside each shell, we have there orbitals. And these orbitals include S, P, D, and F. There are 4 of them. And they are these orbitals which make up these shells. And actually, there are these electrons that do accommodate these electrons. So it's not that these ones, these electrons, they are just hanging in space. They are just swinging around. No, they have specific places. An orbital is that specific location where you have a high probability of finding an electron. Okay? Yes. So, therefore, these orbitals, they could be S, P, D, and F. Now, the first orbital, you see, it accommodates the 2 electrons. Why? Because it just have 2 spaces, 2 suborbitals, and it is just the S. Okay? So the first orbital is just the S, and the S has 1 suborbital, or has 1 orbital. Okay? And this one can accommodate a maximum of 2. And these 2, they are in opposite. We are going to see the roles. Now this is the 2. That's why in O level you used to write 2 and then 2. 2. Because you are told that the first orbital accommodates a maximum of 2. But now to go deep, it accommodates a maximum of 2 because it is just the S orbital, this S. Now if you proceed, the second, this one, okay, it has 2 orbitals. It has the S and the P. Okay? And the S, it is just like this. It accommodates a maximum of 2 because it has 2 suborbitals. But the P for it can accommodate a maximum of 6 because it has 3 suborbitals. That electrons, two of them can occupy here, okay? And also the other
I'm
2,
confused.
you are confused. I know because I'm trying to introduce a new concept, okay? So let me begin afresh because that's why you are in Form 5. I'm trying to introduce a new concept. That in Senior 2 you were told that this is how we write an electronic configuration. That this is of nitrogen, it is just 2 to 5. Why? Because the 2 electrons will occupy the first orbital, then the proceeding can accommodate a maximum of 8. And which 8? It is, yeah, the maximum of 8. And here I want to show you where the 8 comes from. Now, since this one has 7, the 2 will occupy the first. Then the remaining, since they are not 8, the remaining will occupy the next orbital. Okay? Yes. Now, so that's what happens. If you are to fill them, you put 2 here, another 2, and 5 of them here. But now this is 2 general. This is 2 of O level senior 2. But now here, we try to magnify deep. Okay? We try to magnify. Let me see. However, if we try to magnify deep and see what is inside these shells. Okay? What is inside these shells? Actually, atoms have very many shells, not just 2. You can have a nucleus, and you have this, the first shell, the second shell, the third shell, the fourth, the sixth, and so, because imagine, how are you going to write the atomic number, the electronic configuration of an element with 90 as its atomic number? Can you imagine? So you'll be able to find that you have very many shells. Okay? Yes, that's pretty good. So now, if you magnify deep into these shells, you'll be able that if this is a shell, you'll be able to find that this shell has other subshells called orbitals. Okay? Yes. Even the preceding one, it also has other subshells. Okay? Even if we put another one, it also have some other subshells. Okay? It's not just this. Even when we put another one, even when we put another one, it also has other subshells. Okay? Whereby the first, it is just the ace. Okay? It is just the ace. Okay? This one. And the ace accommodates a maximum of 2 electrons, and that's how we write electrons. This is electrons
Teacher
1.
is the first cell is the one which has the ace. Eh?
Yeah, the very first, the one which is close to the nucleus. Okay? It is the one which is the s orbital. Now, as you proceed, as you go away from the nucleus, then you form other orbitals. Now, the second one, the second shell, for it has both the s and the p. Okay? And the third, for it has both the s, the p, and the d. Can you imagine? And the fourth shell, if we continue, this was the first shell, this is the second shell. Now the second shell has both s and p. The third shell, the one I've just drawn, for it has both s, p, and d. Now if I draw the fourth, this one, okay, if I draw the fourth, now for it will have, the fourth shell has both s, it has both p, it has both d, and it has both f. Now the rest, the proceeding, if you have more, they just stop at f. Okay? Are you getting me? It's okay, you can always unmute and say something. So that's basically, if we try to magnify deep, so basically that's what you see. So you see that if this second shell, it has 2 subshells, the first one and the second one. Now this first one, it will be the s, the second one, it's the p. If we try to draw another one, maybe this is the third shell, it will have 3 shells. The first shell, which is the s, the second one, which is the p, and the third one, which is the D. Even when we proceed to the next, it will have now more. Where the first one, this is the S, then P, then D, and then F. And the same applies to the preceding shells. Okay? So by this, there are now these shells. There are now these subshells called atomic orbitals that will have space which will accommodate the electrons. Is that okay? Yes, that's pretty good. So they are the ones with space where electrons will occupy. And so if we consider the S just have one suborbital. Okay? One like this. And the electrons will occupy, and each suborbital like this accommodates a maximum of 2. And the 2 they are in parallel spins, but opposite, like how we are going to see. But the P, if you proceed to the next energy level, this one, and the next energy level has both the S, okay, and P. So the S has its one orbital, but the P has its 3. Are you seeing? Has this one, and it also have this. So the S accommodates a maximum of its 2, and this P, each orbital accommodates a maximum of its 2. Like this, like this, like this, like this. So if this one, therefore the P will accommodate 1, 2, 3, 4, 5, 6. So this one accommodates 6, but this one accommodates 2. So 2 plus 6, that's 8. So do you see how in order for you to write, for example, calcium, which is 20, in order for you to write 2 to 8, now this is the 8. To another 8. Now I'm going to show you another 8. Okay? And finally, yoka 2 here. That this is the electronic configuration of calcium. But in A level, here we go deep and we use these orbitals as we are going to see. Okay? For the 3 which has both P and S and D, let me do the cleaning. For the 3, it has both S, P and D. The S will come with its one orbital, okay, filled up with electrons. The P will come with its 3, 1, 3, filled up with electrons, like this. Now this should be at your fingertips. And the D will come with its 5. Now the D has 5. So it's like if here is 1, then it will be plus 2. So the D has 3. Then plus 2 again. Okay. D has 5. So it is 1, 2, 3, 4, and 5. So this is D. So the electrons will occupy this parallel but in opposite spins. We are going to see. I hope you should be thinking about F. So how many will F have? So this is the D. Now the F. Yes. Can you guess the F? Yes.
7.
You've guessed right. So the F we just add 2. So the F has 7 suborbitals. So you draw 7. Okay. So do you see that the F accommodates a good number? So that is 1, 2, 3, 4, 5, 6, and 7. So now the electrons, they will occupy these orbitals singly, and then pairing occurs. Now what I'm doing here, it's not how we do it when we are writing electronic configuration. We shall reach there and you study. So basically that's how. So this one therefore, This one will accommodate. So the ace will accommodate a maximum of how many? 2. So the first orbital accommodates a maximum of 2. Now the second, the p will accommodate a maximum of 6. That's pretty good. And the d can accommodate a maximum of 10. I hope you know where the 10 is coming from. Yes. And finally the f. Can you guess? The f will accommodate a maximum of how many? Yes. Yes, you've guessed right. A maximum of 14. Because this is 7 times 2 electrons each orbital, which is 14. So it is basically as simple as that. Now, once you understand this concept, then everything becomes easy for you. Once you understand this concept, everything becomes
Teacher,
easy for you. Yes.
so again, why did you multiply? Why are you multiplying again?
By 2,
Is that two?
it is
Hmm.
here. They are 7 orbitals. 1, 2, 3, 4. You can mute again. You mute. 1, 2, 3, 4, 5, 6, 7. But each orbital has 2 electrons. Okay? 2, 2. Even here 2. Even here 2. Now you must, I repeat, you must know these rules. Not by cramming, but by understanding. Me, I hate cramming, and I hate students who cram. In A level, no cramming, we understand. So rule number 1, it says that the electrons in ground state. Oh, I didn't talk about ground state. I didn't talk about ground state. Now, ground state means it's like, let me illustrate it using this. Like right now, assuming you join a rotary and you win 200 ma, okay? You win 200 ma right now. Like right now. How will you react? I know, be excited. Spend the money, dash, give your birthdays, go out, do all stuffs. But eventually, the 200 ma will get used up and you come back to 0. Okay? Now, the way you behaved when you had the 200 ma, is it the same way when you're going to behave when you have your 0? Automatically, no. So here, with a 200 ma, you are in an excited state. You are too excited. Okay? That's why you're dashing out money like SARS. I don't even know. But here, when you have 0, then you are cool, you are a good boy, you are a good girl, you do work you do housework. Mommy calls you, you reply when you are humble, like you are really good. Okay? So that's what we call the ground state. Here you are at your ground state. So the same applies to this. So when these electrons, okay, when these atoms receive energy, the electrons are promoted to high energy levels. So they become excited. But eventually, that energy is given off. Okay? And the electrons come back to their normal positions. So there, we call them, they are in their ground state. So in other words, an element in its ground state is called an atom. Okay? But an element in an excited state is an ion. Okay? So basically that's how.
Teacher, pardon.
An element in its ground state is called an atom, but an element in its excited state is called an ion. Is that okay? Yes. So when you are writing electronic configurations, usually we first write electronic configurations of atoms, that is, elements in their natural ground state. But you can also write the electronic configuration of an ion, as we are going to see. So, and the rule number one is called the alpha Bowels principle. This is someone's
Teacher,
name. Yes,
you said we have the ground state and what other state?
excited state.
Okay.
Okay, so we have the alpha Bowels principle. This is someone's name. So he did research and came up with a principle of writing the electron configuration. And he said that the electrons in the ground state, they occupy orbitals. Which orbitals? The S, the P, and the D, and the F. These orbitals. These electrons occupy these orbitals in the order of increasing orbital energy levels, whereby the orbitals at lower energy levels are filled first. So it is as simple as that. When these orbitals, when the electrons are occupying these orbitals, they do occupy them in the order of their increasing energy levels, whereby the orbitals at lower energy are occupied first. And so we came up, actually the closer to the nucleus, the lower the energy. And the farther away from the nucleus, the higher the energy level. So those ones which are close to the nucleus, they are occupied first.
So you are first. You are first.
I'm first. It's okay. I'll try to repeat myself as
The,
many times
the
as
closer to the nucleus.
you are lost.
Yeah, like from where? The closer to the nucleus, the what?
Oh, the lower the energy. And the farther you are from the nucleus, the higher the energy. I'll always repeat myself, so there is nothing to worry about. So if this is your nucleus, these energy levels which are close to the nucleus have low energy, and these ones which are farther away from the nucleus, they have a high energy. In other words, they are at high energy levels. So as a result, he came up with an order, okay, at which these electrons will occupy these orbitals. And the order is this, okay? 1s, okay? You arrange them, okay, in this order where the electrons will occupy in that order. Maybe let me write it. Oh, sorry. Oh, okay. I thought it had some animation. Let me do the cleaning because we learn better when the teacher is writing. So this is 1s. This is how you arrange them. So the first energy, the first, now there is a word I'm going to say but I haven't introduced. The first principal quantum number. Okay, the first period. That is good. Periods, they are these ones. Okay, on a periodic table we have period 1, period 2, period 3, period 4, and so on. And from O level you were taught that these periods refer to number of shells. Not so? You remember that? If I write 2 to 8 to 1, this one has 3 shells. 1, 2, 3 shells. So therefore it will be in period 3. You remember that work in O level? Yes, that's pretty good. Now, the first period has just one s orbital. The second period it is named as 2, but it has the 2s orbital and the 2p orbital. The third period, it has the 3s orbital, the 3p orbital, and finally the 3d orbital. Is that okay? The fourth period, it has fourth s. It has 4p. It has 4d, and it also has 4f. So it is as simple. Then the proceeding, they just have the f. The 5, it will be 5s. This is s, not 5. Then 5p, 5d, and then 5f. Now the f doesn't change. Oh my god. The f doesn't change. 6, it will be 6s. Once you reach f, then you don't have d. E, F, G, you don't have G. No, it stops there. This is 6s. This will be, what is this? Yes, 6p. What's next? 6d. That's pretty good. And finally, 6f. 7 is still the same thing. Now, when the electrons are occupying these orbitals, they are going to occupy them in that order of increasing energy levels, increasing energy. Where the s being close to the nucleus, it will be occupied first. Then they occupy this. Then they go to 2s, then 2p, and then 3s, like this. Okay, and then from 3s, then they go to 3p. Okay, then from 3p they go to 4s. Now from 4s they go to 3d, like this, then 4p, then 5s. That's the order. Then from 5s they go to 4d, then 5p, then 6s. That's the order. Then from 6s they go to 4f, then 5d, then 6p, then 7s. 7s is somewhere here. So and so on. So that is the order that is followed. So when I'm writing, let's write some order from this. Let's write some order. Let me clean up so that I use here. Let me clean up so that I can use here to write. So I'm writing the order from this. Okay, let me use another pen. Direct. I'm writing this order, the order how it is going to be from this. So it will be 1s, 1s, then 2s. Can you guess the next? You guess. Yes. This is from 2s, then you go back here. So it will be 2p. Okay? Then from 2p, you don't go here, but you go here. You follow the arrow. Then you go to 3p. Now now somebody wants to put 3d. If you put 3d here, I'll cross you. Now once you go to 3p, where is 3p? 3p, and you go to 3d, I'll cross you. But you continue with this arrow. Then you go to 4f, 4s. Okay, sorry for the handwriting, but I'm using a laptop to write. Then from 4s, then you go back, yes, to 3d. So you write your 3d here. Then from 3d we go to 4p. So that is the order. Guess the next. Yes, that one. 5, 5, 5s, from 5s, then you go to 4d. Are you seeing? So that is the order that should be maintained. Is that okay? And so on and so on, depending on the atomic number, depending on the electronic configuration that you are writing. Is that okay? Is the alpha Bowels principle okay? Any question for us?
Yeah, teacher,
Yes.
why didn't you also cross out the 5F and the 6D?
5F and the 6D because I just wanted to stop here. But the order continues. Now, if this is 7S, okay, just that my space was limited, but somewhere down there, you'll have, this is 7S, this will be 7P, this will be 7D, then this will be 7F. Then somewhere down there, if you are using a book, you have 8, but can you go up to 8? How many periods do we have? I think it's 7. So still the order will be the same. So you come and do this. This is the occupy 6F. Is this no 5F? Then 6D, then 7P, then 8S if it is there down. So basically that's, then from here they go to this, and finally they occupy the 7F. So basically it is as simple as that. Not so? Yes. Now let's go to another rule. On assumption that this one is okay, it must be okay. If something is missing, if something is lacking, then the other rule is going to give you a bloody nose. Yes, orbitals. It is, this one is good, and you need to be as attentive as possible, basing on what we studied on the previous slide. And this one states that an orbital contain, so they cannot contain more than 2 electrons, and these 2 electrons must be in parallel but opposite spins. Spins, I mean, if this one faces up, then the other one must face down, but they are parallel to each other. And you cannot put more than 2, okay? You cannot put more than 2 electrons in one single orbital. And good enough, we have an illustration here. So here we are using carbon. Can you guess what's the atomic number of carbon? Guess, guess, guess. Yeah, you've guessed right. It is 6. So in whatever you studied that, it will be 2. 2. That's pretty good. So now we can write our electron configuration of carbon as this. This is the first electron. This is the second electron. Now these ones are in 1s. Now the P, we still have the same thing, okay? Sorry, the 2s, it is 1s, then the 2s, it is still the same thing, the 2 electrons. But now when it comes to P, some of you might want to put this one here, okay? And then you put another one here, like what you are seeing here. This is wrong. If you do this, this is wrong, okay? You cannot contain 2 when others are still empty. At least let this one be empty, but when you don't have 2, you just have half. So like how you sing here. Number 2, Some of you might put this like how you put like this. You are seeing this one. If you write number 3, it is not correct. Why? Because when these ones are not in opposite spins. Because when I fill this one with an electron, it will be like this. But now, you see, if you compare this electron and this one, these two, are they really opposite? No, they are not opposite. So since they are not opposite, this one is wrong. Okay? But if I write this, you can see, if I put another electron here, automatically these two are in opposite. Even these two are also in opposite. Okay? If I put another one here and I put it facing downwards, this one is wrong because these two are not opposite. Sorry, no, if I put this one down, it is okay. But remember, if it comes pairing, I'll put this one up. Okay? So if this was facing upwards, then they won't be facing in opposite side. So in simple terms, electrons must be in parallel but in opposite spins. Is that okay? Is that okay to all of us? Anita, Edwin, is that okay to all of us?
Not very well, eh?
Okay. Let me repeat. I always repeat myself. You can mute. Let me use sodium. What is the atomic number of sodium? Can you guess? Can you guess? Can you guess? But don't speak. Can you guess? Yes, it is 11. You've guessed right. Now, this 11, it will occupy the electrons. These electrons, they must fill the orbitals. And so when they are filling the orbitals, they follow this Pauli's exclusion principle. And basing on our alpha bow, this order, this will be the order of filling. Okay? The orbitals. That's the order. I repeat, this is the order. And so, basing on that order, we can write. Remember, it is the first 1s. You can guess with me. 1s, and then followed by, yes, 2s, followed by, can you guess? Can you guess? Yes, followed by 2p. Then can you guess? Can you guess? Followed by 3. Yes, 3s, you've guessed right. Followed by, yes, 3p. And so on and so on. This one will be enough for us. Now, the sodium having its one electron, let me first draw these orbitals so that we can fill them together. Yes. So this is 1s, this is 2s. Now I'm going to draw the 2p. 2p is kinda elongated because it has 5 orbitals. Sorry, 3 orbitals. Yeah, so that is 2p.
Teacher,
Yes.
can you please help me and take me back to the previous slide? Show us the previous
You want
slide.
this order.
Mhm.
So that's the order. You can write it down. So that's where I got the other order.
You are bringing 3p again, 3a, something like that. That's where I'm confused
No,
from.
it is
You
3s
are-
first, followed by 3p. You see? 3s is here. Okay?
you put back on the other slide and you see.
It's there. So it's like this. 3s is here. So when you reach here, can you please mute? Then you go back. Okay? So it is 3s followed by 3p, then 4s, then 3d, 4p, 5s. Is that okay? Yes. So that's why our order is like this. So this is the 2p orbital. The 3s, it is always like this, just one, and then the 3p, it is always like this, three of them. Now, since sodium has 11 electrons, these 11 electrons are going to occupy these orbitals. Okay? And they first occupy singly as a single, and they are going to occupy, since this one accommodates a maximum of 2, it will be filled up. Okay? And that is 1s, 1s. And since there are 2 electrons, we write the 2 here. Then the 2s, still same thing. So this is 2s. 2s2. What is the number of electrons you've used? You've used 4. So what is the balance? Yes, the balance is 4. 11 minus 4, the balance is 7. So you still have a balance of 7. Now out of these 7, they are going to occupy this.
Excuse me, sir.
Yes.
Where is that squared coming from? I've not understood.
Okay, let me first rub the squared. I'll talk about it. Let me first rub the squared. I'll talk about it, okay? 1 is, sorry, this is 2. But anyway, let me talk about it now. Now, the squared refers to the number of electrons in this orbital. Okay? So you have 1, 2 electrons. So that's why you write a 2 here. Here in the 2s, you have 1, 2. That's why you write the 2 here. Not so? Now, we have a balance of 7 because we have used the 4. 4 minus 11, we have a balance of 7. Now, this 7, they are going to occupy the next orbital. And the next orbital is the 2p. And the 2p, they are going to first occupy singly. This one goes here. This one goes here in the same spins. Okay? Now, when the whole of these ones are occupied, okay, now pairing begins. Okay, now they pair. We have used 1, 2, 3, 4. But remember, we have our 7, so we still have our balance. 5, 6. So we still have, we have, out of 7, we have used the 6. So we have our balance of 1 electron. Don't forget. Okay? So now, since this one is occupied fully, then you write 2p, and a 6. 6 means the number of electrons in this, and you have 1, 2, 3, 4, 5, 6. So do you see that they are all parallel? And you see that they all have opposite spins? Yes, that's pretty good. Then the next thing is the balance. The balance occupies the next orbital. And the balance is just 1 electron. And the 1 electron, we shall put it here, like this. Is there any balance? Is there any other electrons? No. So it will just be like this. So it will be 3s. And the s has 1 electron. So it is as simple as this. Now we can rub this. We don't need this. You don't need to write it. Okay? So I can rub it. So literally that is how we write. when the rest, can you please mute? This one has 2, when the rest don't have. So that's why it is wrong. Which is this rule? The Handy's rule. Okay? It says that the the orbitals of sub-energy level must be occupied singly. Singly means single. They must be occupied singly first and with parallel spins before pairing occurs. And you can see from here, this is wrong because they had the blue electrons. You see this, and you see this, and you see this. Okay? So they first used, anyway, this one might confuse you. Let me first use this before we advance. So you have, let me use the P, okay? These are my 3 p orbitals. Now for you, instead of writing the electron configuration, maybe you have 4 electrons available. Okay, not 4, but you have 2 electrons available. Now instead, you do this. You write, you put 1 here, you also put 1 here. This is wrong. Okay? This is wrong. But this is what is correct. They first occupy singly. Single. Okay? And when the electrons are still available, then they pair. So you first put 1 here, and then you put another one here. So if you do this, this is wrong. But if you do this, this is correct. Okay? Assuming you have 4 electrons. Okay? 4. And instead of 4, this is my p orbital. And you have your 4 electrons. And instead of writing normally, you just do this. You put 1 here, you put another one here. You put 1 here, you put another one here. Now, this is wrong. Okay? They first occupy singly before they pair. They first occupy as singles before they pair. Okay? So this is how it is done. You first put here 1, you put another one here, okay? You put the 3rd electron here. Now, since you have a balance of 1 electron, then that's when it will come and pair up with this one. So it is as simple as that. If you write this, I'll cross you. But if you write this, I'll mark with 1 hand. If you write this, I'll cross you. But if you write this, I'll give you a smiling tick. Is that okay? Is that okay? Anita, Edwin? Edwin? Is that okay? Please unmute and talk.
Yes.
It is okay.
Maybe if we go further, things will become
It's okay, don't worry.
clear
They'll be okay.
at
Edwin?
some point.
I hope it is okay. So let's do some 3 examples, and then you go to our classroom and do work. There is some work there. Let me get I want some free space where I can write. Maybe let me go and borrow a slide in chemistry and biology. I just want a free slide where I can write. So don't mind about this. Don't mind about this. I just want a free slide where I can write. So now we are going to do for 17, and then we do for 20, and then we do for 25. Okay, so we are going to do these electronic configurations. Okay, we can also do for 29. Okay. So from the other order vowels, don't forget that order, the alpha bow. Actually, before you even do any electronic configuration number, you should first write the order 1s. Actually no, the 1s is here, then 2s, then 2p, then 3s, 3p. This order is so important. You should be writing yours with mine. Then 3p, from 3p, then we go to 3d. Then what next? Yes, 4s. Then from 4s we go to 4p. Then from 4p we go to 4d. Then from 4d we go to 4f. I hope this will be enough for our electronic configuration. So now the order of filling. So always first write this one. The order is like this, then followed by this, then followed by this, okay, followed by this, and then finally this. Maybe you have the 5s here, and so on. So that will be the order. Okay, this is the order that we are going to use to answer this question. Now for 17, that one is chlorine. Okay, and so when you are writing the EC, it will just be from here. The 1s occupies how many? 2 electrons. So we shall write 1s2. Okay, what is the balance? So out of 17 we have used 2, so we have 15. So we still have more. Then we go to 2s. 2s. Then the 2s also occupies how many? 2. So we have used the 4. We have a maximum of, now we have a balance of 13. So we still have. Then we go to 2p, and the p can accommodate a maximum of 6. So now we have used 2 plus 2 plus 6. This is 6. So that is now 10. Okay? Now 10, 17 minus 10. So you have a balance of 7 electrons. Not so? Now since you still have more, then you go to the next level. 2p, now we go to 3s. So we shall go to 3s. And the s accommodates a maximum of 2. So this is 3s2. Now you have a maximum, you have a balance of 5. Since you still have more, then you proceed to the next, and the next here is, yes, the 3p. So this is 3p. And p accommodates a maximum of 6. But you see, we have a balance of 5. So it means all the 5 will occupy the p orbital. And that is the electronic configuration. Anita, is that okay? Edwin, is that okay? Mm-hmm. Anita Edwin, is that okay? The electronic configuration?
If possible, you can repeat for us that of chlorine.
I repeat that of chlorine, but we shall do for calcium, the one of 20, and it is the same way. Anita, I want to hear from you. Anita?
Yes.
Yeah, is the electronic configuration okay?
No.
It is not yet okay. So, no, don't worry. So, that is for chlorine, eh? And I've gotten it from this this order. So, if you can write this order and from these arrows, then everything will be okay. So if I repeat for chlorine, it has 17 as its atomic number. So meaning it has 17 electrons. And there are these electrons that do occupy the orbitals. Okay? Yes. Now they will first occupy the 1s because it is the one that is close to the nucleus. Now that is, they will occupy it and fill it. Those are the two. These two means the two electrons. Maybe let me use boxes. Maybe boxes can be understood better. To try to illustrate. So this is the
Teacher,
one
boxes confuse more.
the boxes confuse more. Okay. Okay. Let me use. Uh-huh. So this is the 1s because this is the one which is close to the nucleus. Then it will be occupied by the two electrons. Okay, and it fills up. Then this is the 2s because it is the one which follows. You can see. Okay, from this. So you write the 2s, and the 2s will be occupied by the two electrons. Then followed by the 2p because you can see p's.
Teacher,
Yes,
I suggest
yes.
that why don't you draw for us the diagram for chlorine? Like
And you want us
it
to.
shows, and show us how it is coming to, because I'm saying we are only following the table, this one that we have drawn aside,
Mm,
but on chlorine,
mm,
because when if I'm writing its electronic configuration, as
mm.
we used to write in O level, we used to write like 2 to 8 to 1, not so.
2 to 8 to 1. That's
So then I'm wondering, I only understood how the 1s2 came to be, because the first shell has 2 electrons, but the following shell has 8. Now I'm confused
I
why
know.
we are having this.
I know it's
Yeah,
okay.
like
I know. Don't worry. Let me first take away this. Now, I hope I can erase everything. I can't. Now, from O level, oh god. So from O level, we are told that chlorine, if this is the shell, that will be the nucleus, and this one is the first shell, and it accommodates a maximum of 2. Not so? And then this is the next shell, and for it accommodates a maximum of 8 electrons, and these 8 electrons are in pairs, like how you see. Okay, pairs. Then so it is 2 to 8. Then to 8, is it to 8 or to 7? So if you add 2 plus 8, that's 10, so it is to 7. So isn't what you are told in O level? Yes, that is good. Now I told you that in O level it is summarized. Okay, it is summarized. We just give you a brief summary, but here we go deep. We try to magnify these orbitals and see what is inside. Okay, that if you try to observe, you find that the one that is close to the nucleus, that first orbital, in O level you were told that it accommodates a maximum of 2, and here it is just the 1s orbital. Okay, and the 1s orbital, it accommodates a maximum of 2 electrons. One is there and another one is here, so that is why you're seeing the 2. Okay, and that's why you're seeing this K2 here. But now the next, they told you that it accommodates a maximum of 8. But if you try to, like I told you, this one, it has both the S and the P in it. But in O level, we just summarize the S and the P into one shell. But it has 2 subshells. Okay? One, it has the S and it also has the P. So those are the 2 S, okay, and the 2 P subshells. Is that okay? But that S, we have told you that, or we have agreed that the S can accommodate a maximum of 2. And the P can accommodate a maximum of 6. So when you add the 2, don't you get 8? And so this is the 8. So this, whatever it is 2, to 8. So this is the 8. Okay? This second shell. Okay? Now the third shell, they told you that it can accommodate also 8. But actually it goes beyond 8. That it has 3 sub-levels, sub-shells. It has 1, 2, and 3. So the 1 is the 3s, the second is the 3p, and the third one is the 3d. Can you imagine? It is the 3d. So electrons, when they are occupying, they occupy the 3p, so the 3s, and then 3p, and finally 3d. Whereby this one can take a maximum of 2, but this one can take a maximum of 6, and this one can take a maximum of 10. But you see, our chlorine being 17, it will use 2, okay, then another 2 here, so that is 4, and the 6 here. So when you add, that is already 10. So what is the balance? The balance is 7. So out of 7, 2 will fill the S, because it comes before the 3p. You can say 3s, then 3p. And then, so if 2 occupies the S, out of 7, the balance is 5. But remember, this P needs 6, but there is only 5 available, so that's why we shall put the whole of this 5 here. Okay? And you ignore this, because it is not needed here. Is that okay? So can somebody mute and tell us if it is okay? Anita, I hope it
It,
is.
it is okay.
Good. Anita, I hope it is okay. Anita,
Yes, teacher.
I hope it is okay now.
Yeah.
That is good. Now, you're going to write down the electronic configurations of these ones. The 20, 25. Don't write 29 because it is hard. You won't do it. Okay? Let me give you more work. In fact, the work is simple. You write from 1 up to 25. No, up to 30. Even you do this because you understand the concept by doing. You write from 1, but it might be hectic, it might be too much. Okay, you write 9. Okay, you write electronic configuration of, okay, nitrogen and atomic number is 7. You write the electronic configuration. I'm giving you work. Let me clean. Oh, they can't be cleaned. Nitrogen and atomic number is 7. You write silicon and atomic number is 14. You write chromium, Cr, Ch. Is it C? It is Cr. Cr and atomic number is 24. You write manganese and atomic number is 25. You write